ठीक है, स्टार्ट करते हैं अभी, है ना, ज्यादा टाइम नहीं है हम लोग के पास आज, तो स्टार्ट करते हैं।
या ओके सर।
आ रहे हैं बाकी बच्चे?
सर आप स्टार्ट करो, मैंने ग्रुप पे लिंक ऐसे भेज दिया।
ओके। Okay, so in last class we were on the equation of motion. So equation of motion is basically the second axiom of the thermodynamics, which tells you that the momentum is conserved. So we have just generalized the equation, this equation for the for a rectangular control volume, then develop a equation which can be used as a for the solving any problem, and you can use the equation of motion to solve any problem. So this is the generalized form of equation of motion. The equation number 17, equation number, then this is equation number 18, and equation number 19. These are the different form of equation of motion. So these are most generalized form of equation of motion. Okay, so you need not to you need not, you are not taking any assumption during the derivation of these equations. Okay, so for every problem you can use these equations without any correction. Okay, so basically these equation can be used for Newtonian fluid, for non-Newtonian fluid, for compressible fluid, for non-compressible fluid, all type of fluids, for all type of fluids, for this equation can be used. Even these equations can be used for the isothermal systems and for the non-isothermal systems. Okay, now we will see the now we will derive a limiting case for the equation of motion, which is the Navier-Stokes equation. Okay, so Navier-Stokes equation is the limiting case of the equation of motion when we assume that fluid is incompressible and follows the Newton's law of viscosity. Okay, so Navier-Stokes equation, where for incompressible Newtonian fluid. Okay, so basically Navier-Stokes equations tells you for deriving a Navier-Stokes equation, you have to take the two assumptions. First, the fluid is incompressible. Second, the fluid is Newtonian. So when you apply the Newton's law, then you can replace this shear stress term, tau term, to the Newton's law of viscosity. Okay, so what is the Newton's law of viscosity? So for the one-dimensional system, Newton's law of viscosity can be written as of viscosity. For 1D system, you can write tau yx equal to minus mu d del vx by del y. This is the Newton's law of viscosity for the one-dimensional system. But this equation is generalized for the 3D system. This equation of motion is derived for the three-dimensional system. Okay, so you have to use the three-dimensional form of the Newton's law of viscosity. Okay, so the three-dimensional, for the three-dimensional law, first In the 3D system, tau is a tensor quantity which has the 9 components. So what are the components of tau? Tau xx, tau xy, tau xz, tau yx, tau yy, tau yz, tau zx, tau zy, and tau zz. So these are the 9 component of shear stress. Okay. Now in these components, tau xx, tau yy, and tau zz are the normal stresses, and others are the shear stresses. Tau xx, tau yy, and tau zz are the normal stresses. Okay. Now before substituting the equation, Newton's law of viscosity in the original equation, first we will use the third axiom of the transport phenomena here. So the third axiom is the moment of momentum is conserved. So we will use this third axiom here, that tells you that moment of momentum is conserved. Okay, so the basically I am not going to the mathematics of the third axiom. I just write the final result or final conclusion of third axiom. So basically, when you do the derivation, so this axiom tells you that the shear stress is a shear stress tensor is a symmetric tensor, is symmetric in nature. Okay, and what is the meaning of the symmetric tensor? When a tensor is a symmetric tensor, then tau ij should be equal to tau ji. The magnitude of the tau ij should be equal to tau ji. Okay, so the moment of momentum is conserved. That tells you that tau xy should be equal to tau yx. Similarly, tau xz should be equal to tau zx, and tau yz should be equal to tau zy. Okay, now if now I am writing the generalized form of the Newton's law of viscosity in the three-dimensional system. Based on this, we will write the generalized form of Newton's law of viscosity in the three-dimensional system. So Newton's law of viscosity in three-dimensional system. So in the three-dimensional system, you can write tau equal to, this is the Newton's law of viscosity, minus mu del plus 2 by 3 mu del dot v del ij del I del j. This is the Newton's law of viscosity. Basically, this equation is derived from the axiom 3. Okay. So, where del equal to, this del equal to del Vi divided by del Xj plus del Vj divided by del Xi del I del j. This is equation number 19. This is equation number 20. This is equation number 20 and this is equation number 21. Okay. Now if you want to expand this equation, then I can tell you what is the equation, basic equation. So if you expand this equation, you will get tau xx equal to minus 2 mu del Vx by del x plus 2 by 3 mu del dot V. Okay. And tau yx tau xx, then tau yy. Then second term is tau yy. First I am writing the normal components. Tau yy equal to minus 2 mu del Vy by del y plus 2 by 3 mu del dot V. Then tau zz equal to minus 2 mu del Vz by del y plus 2 by 3 mu del dot V. So these are the normal components of the shear stress.
सर डेल जेड नहीं होगा?
हाँ, del z. This should be z. Okay. These are the normal components of the shear stress. Now the shear component, normal component of the stress, not the shear stress. Now this is the normal stresses. Now we will write the shear stresses. So the shear stresses are, because it is a symmetric tensor, tau is a symmetric tensor, tau xy equal to tau yx, and that should be equal to minus mu in bracket del Vx by del y plus del Vy by del x. Similarly, tau yz equal to tau zy, that is equal to minus mu del Vz divided by del y plus del Vy by del z. Then third component is tau xz equal to tau zx, that is equal to minus mu del Vx by del z plus del Vz by del x. So these six are the, basically these are the six components. These are the shear component. Okay. Now, suppose you are solving the problem where fluid is flowing between the two plates and Your velocity is in the v direction, where this is the velocity which is in the y direction only, and this is the x direction. So you can write on, you have the velocity vy which is depending upon x. Okay, so then you have to write the tau yx. So when you write the tau yx, then you have to use this equation, है ना? So in this equation, because vx is 0, the first term will be 0, you will end up with minus mu dvy by dx. So you will get the one dimensional equation of the Newton's law. Okay, the equation is same, because if you are using the two-dimensional flow, then you have to use this original equation. Okay, so basically these are the, if you are coupling the all equations, all six equations, then it is a three-dimensional flow system. Okay, now we have to write the, in the equation number 19, you have the del dot tau. Okay, now again we will do the material balance for the x, the momentum. Okay, because initially we work on the x momentum balance. This is the x momentum balance, so we will solve the x momentum balance only. Okay, so for x momentum balance, for x momentum balance, you can say minus del dot tau in bracket x. So that is equal to, in the x momentum balance, it will come as in bracket del tau xx divided by del x plus del tau yx divided by del y plus del tau zx divided by del z. So this is from equation number 11. From equation 11, if you go to the equation 11, you can see this is the same term we are writing, tau xx by del x, tau yx by del y, tau zx by del z. Okay, so this is the x directed momentum balance. So this is the shear stress term in the x directed momentum balance. Okay, now what we will do, we will substitute the values of tau xx, tau yx, and tau zx from the Newton's law of viscosity. Okay, so when you substitute first tau xx, so what is the tau xx? Tau xx equal to minus 2 mu del vx by del y plus 2 by 3 mu del dot v. Okay, now here we are also assuming at constant. Okay, first we will substitute, then we will see. Okay, so first we will substitute the value. So then minus del dot tau x, that should be equal to minus in bracket del by del x in bracket, you will get minus 2 mu del vx divided by del x plus 2 by 3 mu del dot V. Okay, plus del tau del by del y. Now you have to substitute the value of tau yx. Okay, so the when you so what is the value of tau yx? Tau yx equal to minus mu dvx by dy plus dvy by dx. Okay, so here you have to substitute del by del y in bracket minus mu, again bracket, del vx by del y plus del vy by del x, bracket close. Okay, now second bracket close. Okay, plus third term del by del z, again in bracket you have to substitute the value of tau zx. So tau zx equal to minus mu dvx by dz plus dvz by dx, minus mu del vx by del z plus del vz by del x. Okay, so you will get this equation. Now in this equation, now we have to first we will open the brackets. Okay, once you open the brackets, you will get minus del dot tau x, that should be equal to, in bracket, del by del x del vx by del x, first term, then you will take mu common. Okay, now plus del by del vx, del by del y, del vx by del y plus del by del y, del vy by del y. So here minus mu will be common. Okay, we are taking minus mu will be common. Okay, then plus del by del x, del vx by del x plus del by del z, del vz by del x plus del by del x, 1 minute, vx vy vx vz. 1 minute, I am again writing this. Del by del x, del vx by del x, this is the 2, so it will come again del by del x, del vx by del x, because here you have the 2 mu x, Okay, now this quantity 2 by 3 plus 2 by 3 in bracket mu del dot v, del dot v, this will come, and here you will have the, this will come under the del by del x. So this will come under del by del x. So del by del x del dot v. Okay. Now plus second term del by del y, del vx by del y, del by del y, del vx by del y. Then next term del by del y, del vy by del x, del by del y, del vy by del x. Next term del by del z, del by del z, del vx by del z, plus del by del z, del vz by del x. Okay. So this is the expansion. Now in this expansion, this term del vx vx, del vy vy, and del z del z, this term will come at one side, so it will become del square vx divided by del x square plus del square vy divided by del y square plus del square vz divided by del z square. Okay, now the remaining terms, what are the remaining terms? This one, and this one. Okay, so you can take del by del x common in all these terms, so it will become del by del x, this will come over common, and again inside the bracket you will have the del vx by del x plus del vy by del y plus del vz by del z. Okay, now the last term is this term, so this is the plus 2 by 3 del by del x del dot v. Okay, so basically this term represent the del vx by del x plus del vy by del y plus del vz by del z. This is equal to del dot v actually. Okay, so del vx by del x plus del vy from the equation of continuity. And when no, this is not from the equation of continuity. This is basically the definition of the del. Okay, so vz by del z, because velocity and del both have the vector quantities. So when you take the scalar product of the vector quantity, you will get del vx by del x plus del vy by del y plus del vz by del z. Okay, so now you substitute this value in original equation, you will get, so this is, suppose this is equation number 22, this is equation number 22, this is equation number 23. Now substitute the equation number 23 in 22. You will get del square minus mu in bracket, this is mu minus mu in bracket del square vx by del x square plus del square vy by del y square plus del square vz by del z square, bracket close. Then you have the plus, this is one more bracket. Okay, then you have plus del by del x del dot v plus 2 by 3 del by del x del dot v. Okay, now in this equation del dot v equal to, now we will take the second assumption. Okay, the second assumption is density is constant. Now if density is constant, then from equation of continuity, you can say that del dot v should be equal to 0. Okay, if the density is constant, then del dot v should be equal to 0. So in the original equation, del dot tau should be equal to del dot tau x should be equal to del square vx by del x square plus del square vy by del y square plus del square vz by del z square. Okay, so basically these are the, this is the del dot tau. Okay, now you have to do one thing, you have to, so similarly you can write del dot tau y, that is equal to del square vy by del x square plus del square vy by del y square plus del square vz by del z square. Similarly, you can write minus del dot tau z, that should be equal to del square vz by del x square plus del square vy by del y square plus del square vz, this is also vy, है ना, del square vz by del z square. Okay, so all these equations you can write in the vector and tensor form. All these equations says that minus del dot tau, this should be equal to mu del square v. Okay, del square is a scalar quantity, so यहाँ पर del square v है ना, del square means del dot del. When you write the del square, that means you are writing mu del dot del v. Okay, so when you take the dot product, it will become the scalar quantity. Okay, now you can substitute this suppose this is equation number 24. Now substitute the equation number 24 in the original equation, which is equation number 20, equation number 19. In this equation, you have to substitute the equation number 24 in equation number 19, del dot tau, value of del dot tau. So when you substitute the value of del dot tau, the equation will become, now substitute equation 24 in equation 19, you will get rho del v by del t capital, this is the substantial derivative, that should be equal to minus del dot p, del p, p is a scalar quantity, plus mu del square v plus rho g. So this is the Navier-Stokes equation. Okay, so this equation is basically the Navier-Stokes equation. This is equation number 25. This is Navier-Stokes equation. And this is true for the Newton's law when the fluid is Newtonian and the incompressible. Okay, this equation is true when you have the Newtonian fluid as well as the incompressible, like water, like oils. And for water, for oils, you can use the Navier-Stokes equation. Okay, so in the Navier-Stokes equation also, you can write in the other forms also in the Navier-Stokes equation. If you writing the Navier-Stokes equation in terms of simple terms or in simple derivatives, so it will become v dot del v. So this is also the same equation. Just instead of using the substantial derivative, I am using the simple derivative. Okay. So this is also equation number 25, same equation in the simple derivative terms. Okay, so this will be work when you have the Newtonian fluid and incompressible fluid. Okay, for the non-Newtonian fluid or the compressible fluid, you have to use the Navier original equation of motion. Okay, there is a one more form of equation that is called the Euler's equation. So Euler's equation is the equation when viscous forces are zero. Viscous forces are negligible. So when viscous forces are negligible, then the Euler's equation will become del V by del T plus V dot del V equal to minus del P plus rho G. Okay, so the viscous term will be eliminated. This term, viscous term, will be eliminated. Okay, so this is the Euler's equation. So this is used when you have the potential flow. Okay, when the flow is happening inside a channel where the width of the channel is very huge, so the viscous forces are very negligible. Or you are solving the problem for the gases in vacuum, and when the viscous forces are negligible, then you can directly use the Euler's equation. Okay, so these are the three equations: equation of motion, Navier-Stokes equation, and Euler's equation. Equation of motion are used in the most generalized manner. For any condition, you can use the equation of motion. Navier-Stokes equation will only use when you have the Newton's law, Newtonian fluid and the incompressible fluid. And the fluid is Newtonian and incompressible, like water, oil. And for this, you can use liquids, simple liquids, which can flow easily. For that, you can use the Navier-Stokes equation. And for the gases where the viscosities are negligible, you can use the Euler's equation, which tells you where the viscous forces are negligible. Okay, आई थिंक इतना काफी है आज के लिए,
यस सर।
है ना। नेक्स्ट क्लास में से आगे चालू करेंगे।